how does a 100,000-ton ship stop at sea? There are no brakes. None at all. At 30 knots, this ship carries the momentum of millions of tons moving in formation. That momentum cannot be stopped by any brake system ever built. Physics will not allow it. The surrounding ocean is both the obstacle and the only tool available to stop it. 4 bronze propellers, each weighing 30 tons, are pushing every kilogram of that momentum forward. To stop, those same propellers must fight the physics they just created. From the inside, no friction brakes, no anchors at speed, no retarding fins, just water and reversed propulsion. This is the USS Gerald R. Ford, and this is exactly how it stops at sea. The USS Gerald R. Ford displaces over 100,000 tons, more than most entire fleets combined. Everything that stops this ship lives below the waterline, invisible from any direction above. 2 A-1B nuclear reactors produce the steam power that turns 4 shafts and 4 propellers. Main steam turbines convert that power into 260,000 shaft horsepower across 4 propeller shafts. 4 solid alloy steel shafts transmit that torque from the turbines to the propellers at the stern. 4 bronze propellers, each 7.5 meters across, generate the ship's thrust through water. 2 large steel rudders behind the propellers steer the ship and control heading during any stop. The hull itself is a stopping tool. Its wetted surface generates friction drag through water. All 4 shafts are commanded from a single bridge console, full ahead to full astern. An engineering team below deck monitors every shaft, turbine, and power parameter in real time. There is no separate stopping system. The propulsion system and the water do everything. Understanding how momentum is transferred back to the ocean is the entire story of this stop. The stopping sequence begins with the ship at 30 knots, approximately 55 kilometers per hour. At 30 knots, the momentum of this hull exceeds 3 billion newton-seconds of force. The bridge issues the order to reduce speed. The engine order telegraph moves towards stop. In the engine room below, the engineering watch begins reducing steam flow to the turbines. The main steam throttle valve closes progressively. Steam flow to the turbines begins to fall. The turbines lose power and begin slowing. Shaft rotational speed starts falling below full revolutions per minute. The propellers still turn ahead, but their thrust output falls as shaft power reduces. As propeller thrust drops, the hull's friction drag becomes the dominant force on the ship. The hull's wetted surface generates friction drag proportional to speed squared. It increases rapidly. The ship begins losing speed. But at this scale, even strong deceleration takes significant time. The shaft revolutions per minute must fall to a safe threshold before astern power can be applied. Applying full astern power immediately at high speed causes violent cavitation on the propeller blades. Those cavitation bubbles collapse with forces that can physically pit and erode solid bronze over time. Experienced engineers wait for the shaft speed threshold before beginning the transition to astern. Once safe, steam is admitted to the astern turbine stages. The shaft begins reversing direction. The shaft stops, then begins turning in reverse. driving the propeller to push water forward. Water still flows past the blades in the forward direction as the ship moves ahead. That reaction force opposes the ship's forward motion. This is the primary stopping mechanism. All four propellers now drive water forward. Their combined reverse thrust, opposing the ship's motion. The bow wave shrinks. The wake changes. The ship is measurably slowing against its own momentum. Astern revolutions per minute is limited to avoid destructive cavitation. Maximum thrust comes at a controlled speed. Within the cavitation limit set by the ship, all four propellers deliver maximum reverse thrust. From above, the ship's track stretches back kilometers, the stopping distance already accumulating. The navigator tracks stopping distance on the chart. It will extend for kilometers ahead. The bridge team monitors speed, heading, and track continuously throughout the entire stopping sequence. The helmsman makes continuous small rudder corrections to hold the ship's heading during deceleration. The rudders operate in propeller wash, giving control authority even at reduced ship speed. 700 meters and 2 ship lengths into the stop. Speed is now 20 knots. Astern power builds as a head speed falls. Reverse thrust force grows progressively with revolutions per minute. As speed falls, hull friction drag reduces. Propeller reverse thrust remains the dominant force. At 15 knots, the propeller wake now runs forward. The visual evidence of reversal visible. Below 10 knots, hydrodynamic forces weaken. Effectiveness of both hull drag and rudder control falls. At low speed, propellers work in nearly still water. Their reverse thrust approaches minimum. Rudder effectiveness falls sharply below 5 knots. Larger angles are needed for the same response. The ship has traveled over 3 kilometers since the stop order. 0 speed approaching. 2 knots, 1 knot. The residual forward motion arrested by the last of the hull drag. The ship is dead in the water. The stopping sequence took minutes and kilometers of track. The telegraph moves to stop. All 4 shafts return to neutral. The stop is complete. All kinetic energy from 30 knots has transferred into the ocean through friction and reversal. The disturbed water behind marks where the ship's momentum was spent. Kilometers of ocean track. The bridge team reviews the stopping track. Distance, time, and heading maintained throughout. The kinetic energy at 30 knots distributes across hull friction, propeller work, and turbine heat. Every confined water transit is planned around the stopping distance requirement. It is never improvised. Maneuvering data for this ship's current weight and speed is pre-calculated before entering any port. Holding position after stopping requires constant small power inputs to counteract wind and current. What almost nobody knows, this ship needs up to 12 of its own lengths to stop. 12 ship lengths is approximately 4 kilometers, the length of a typical highway off-ramp. The full crash stop takes 10 to 15 minutes from the order to reaching 0 forward speed. The nuclear reactors do not throttle down when speed is reduced. They keep producing steam. Excess reactor steam dumps to condensers. It cannot simply be turned off at the reactor. Managing constant reactor output during a stop requires precise steam valve control throughout the sequence. What engineers never show publicly, The propeller blades during a crash stop are under extreme stress. Each cavitation bubble collapses, with hundreds of bar of localized pressure directly on the blade's surface. The blade skew geometry distributes cavitation events across the blade, rather than concentrating them. Blade thickness profiles are specifically tuned to delay cavitation onset during high-energy astern events. The rudders work in accelerated propeller wash. Their authority exceeds what ship speed provides. Both rudders have independent steering gear circuits. One rudder failure cannot remove directional control. During a crash stop, cavitation can occur on hull brackets and appendages, not just propeller blades. Shaft bracket fairings are shaped to survive repeated crash stop cavitation events over decades of service. Wind and current push the bow off heading as speed falls. Rudder angles must increase. Stopping performance is formally measured in crash stop trials and recorded as a precise design characteristic. Both track reach and head reach are recorded. The difference shows total yaw during stopping. Astern turbine stages sit inside the same casing as ahead stages. No separate machinery required. The shaft thrust bearing transmits both forward and reverse propeller forces directly into the hull structure. Stern gland seals must handle shaft reversal at full speed without allowing any seawater ingress. Propulsion control has multiple independent backup paths. Single component failures cannot stop the sequence. Deceleration force peaks at moderate speed where hull drag and reverse thrust combine most effectively. Stopping distance grows faster than speed. Doubling speed more than doubles the required stopping distance. With 2 shafts lost to damage, the remaining 2 still provide meaningful reverse thrust for stopping. Adjacent propellers rotate in opposite directions. This cancels shaft torque and reduces yaw during reversal. Bilge keels and hull appendages add to total drag. Every surface below waterline contributes. Stopping in the ship's own disturbed wake creates different cavitation patterns than open water stopping. A fully loaded ship displacing maximum mass stops over a longer distance than a lighter one. The reactor core temperature stays stable during a crash stop. Thermal inertia protects the core automatically. The complete stopping system, 2 reactors, 4 turbines, 4 shafts, 4 propellers, 2 rudders. The most common assumption, this ship has giant mechanical brakes, similar to those on any vehicle. That assumption is completely wrong. There are no mechanical brakes anywhere on this ship. Every stopping force on this hull comes from water interaction. Friction, drag, and reversed propulsion. Second assumption, if other methods fail, deploying the anchor will stop the ship quickly. Anchoring at speed destroys the anchor, chain, and bow structure. It cannot stop the ship. Anchoring only works when already nearly stopped. It holds position. It does not stop. Third assumption, slamming immediately to full astern power will produce the fastest stop possible. That assumption is backwards. Staged astern application produces more actual stopping force than immediate full astern. Cavitation at high speed reduces effective thrust dramatically. Staged application avoids this loss. Fourth assumption, nuclear power gives the carrier near instant stopping capability because of its enormous power. Reactor power cannot overcome water physics. The limiting factor is cavitation, not horsepower. A destroyer with far less power stops far shorter. Mass, not horsepower, determines stopping distance. Fifth assumption, All large military carriers must be fitted with dedicated emergency stopping systems. The real solution near ports is tugboats, providing external force the ship cannot generate alone. Every carrier port entry uses tugs. The ship's stopping distance is always planned around this. Sixth assumption: the propellers reverse instantly and stop the ship at a constant deceleration rate. The shaft takes time to decelerate, stop, and reverse. There is no instant propeller reversal. The final knots take proportionally the longest. Drag forces fall as speed falls toward zero. Seventh assumption: ocean conditions do not affect the stopping distance of a ship this large. Following seas push the stern forward. Stopping distance is measurably longer with seas astern. The complete picture: no mechanical brakes, no anchors at speed, no emergency systems, just physics. 2 reactors produce steam continuously. The same machinery that drives the ship forward stops it. The stopping sequence begins on the bridge, a controlled sequence, never an instantaneous event. The shafts reverse. 4 propellers now push water forward. The dominant stopping force has engaged. Hull drag and reverse thrust work together, but 100,000 tons of momentum concedes slowly. Kilometers pass, minutes pass. The ship reaches zero speed. The ocean absorbed all the momentum. The ship is stopped. The ocean absorbed all kinetic energy, every joule from 30 knots. No brakes were applied. No anchors were dropped. Water physics and reversed propulsion did everything. In confined waters, the stopping distance determines the entire approach plan. Nothing is improvised. The stopping system is invisible. The ocean, 4 propellers, and kilometers of patience. How does a 100,000-ton ship stop at sea? Now you know exactly how it works.